In the previous section, we talked a little bit about this definition and this idea of continuity, and we mentioned that all polynomial functions are continuous. So in order to consider that if a function is continuous at a certain point, we need to make sure that we go ahead and include the following three conditions. First of all, the function has to be defined at a. So f of a is defined. We actually can get a value there. The limit also has to exist. So as x approaches that value a, we have to make sure that it exists. And then also we have to make sure that the limit at that equals f of a, which is the definition we talked about in the previous sections. If one of these conditions is not satisfied, then f of x is not continuous, and we have to look at our types of discontinuities. So we have three different types of discontinuities. We have what we call a jump. So that means from the left and from the right, x approaches the value of a, but they don't meet. They're different values, all right? And so the limit of f of x in this case just does not exist, all right? Then we have this idea of a hole where it comes in from both sides, from left and from the right. So the limit exists. But there's a hole at that value. So f of a is not defined itself, but the limit does exist. And so therefore, this is a discontinuity we call a hole. Right. Then we have the idea of a vertical asymptote. And either the limit will not exist or infinite. So f of a is not equal to f of a if it's defined. So if we look at the limit, it's not equal to f of a, which violates the third definition where the limit has to equal f of a. And over here, you can see our vertical asymptote. And vertical asymptotes a little bit different than the actual hole. There'll be a different type of discontinuity, but you'll be able to tell who is who just by the fact of whether the limit exists or whether the limit does not exist. All right, so we want to go ahead and find all the values where this following function f of x is discontinuous, and we want to go ahead and look for all three of our rules of the discontinuity. We want to try to find the limit. We want to try to find it from the left and from the right if it exists, see if f of a is defined, and identify which conditions of continuity are not satisfied. So we're going to look at a is equal to -1 for this following graph. So at a is equal to -1, right here, we go ahead and approach it from the left, and we approach it to the right, all right? But does our limit exist here? Well, here from the left, it approaches 2. From the right-hand side, it approaches 4. And so therefore, the limit of this does not exist. All right. If we look at f of -1, f of -1 is equal to 2. All right. So that does happen. But that limit of f of x does not exist. So therefore, it is has a discontinuity, and this is a jump. Right, for this second example, we want to do all the exact same things, and we see that it is discontinuous. It tells us that, and we want to go ahead and find the limit from the left and right, see if it exists, if it is defined at f of a, and look at what kind of discontinuity we have. So when a is equal to -2, with the limit, as we're approaching from the left-hand side, comes up and we're approaching -1. And if we go ahead and approach from the right-hand side, we also have a limit at -1. So the limit in this case does not exist. However, at a is equal to -2, that function is not defined because there is a hole there. All right. And so therefore, this limit does not exist, and this is our hole. Now keep in mind, if we actually had a function for this, how we could tell if this was a hole or an asymptote will be if the limit exists or not. So in this case, the limit does exist, we just have a hole. If it was an asymptote, that limit would not exist from the left and from the right-hand side. Now, what if we're just given a function instead of the graph, and we have to go ahead and look at our limits and see if we have any kind of discontinuities here. All right, well, you could go ahead and graph any of these functions inside your graphing calculator, but what you're going to find is the calculator does not account for any holes, and if there's an asymptote, you may see it all connected to the asymptote, so it might be a little actually hard to tell in the graphing calculator. If we look at our first function, we have 5 plus x over x parentheses x minus 2. Right, and what we could see here is we have to worry about x being in the denominator, and here we obviously have x equals 0 and x equals 2. Both cause the denominator to go to 0, so both of these values are vertical asymptotes. Now you're going to have to go ahead and check both of these values to see if the limit exists, and you're going to find that the limit does not exist for either of those values because they are asymptotes. If we go ahead and look at our example part B, we have x squared minus 25 over x minus 5. Now here we have a hole at x is equal to 5, right? Because that causes the denominator to go to 0. But we can use a trick we used in 3.1, go ahead and factor the top out, and we could go ahead and get a limit at this value, just like we did in 3.1. And so because we can get a limit at this value, this is a hole, even if you didn't notice it before. So this is not an asymptote, this is actually a hole, all right? And we could go ahead, find our limit, and find out at the end that our limit is 10. If we go to part C, we go ahead and we see this is a nice quadratic function, a polynomial. All polynomials are continuous everywhere, so there is no points of discontinuity. You don't not have to check this because we have already discussed that all polynomials are continuous everywhere. We want to look at this idea of piecewise functions because not only are we always given just polynomial functions or fractional functions, we also have this idea of piecewise functions, and piecewise functions follow different rules for different values of x. And a piecewise function will look a lot like this, where you'll have f of x and you'll have 2 or 3 different values and different areas that this graph is covering. So in this case, f of x is 1. If x is less than 2, so this is going to be a straight line from 2 to negative infinity. It equals x plus 3 if the x values are between 2 and 4, including 2 and 4, and 7 if x is greater than 4. So when x is 4, y is 7, but there's a hole there, but it's going to continue all the way on to positive infinity. All right. And these can be a little tricky to try to go ahead and graph in your graphing calculator. Sometimes you may want to go ahead and graph them by hand. And I like to do that, but of course, then you have to create a table for each piece and see what's going on. But there's a great video here that I'll let you go ahead and watch on your own that could show you how to use the TI-84 to graph piecewise functions. But you do have to provide the holes that are available in there. So see, you're going to have a hole here at 2. For this piece of the function, you're also going to have a hole here at 7 for this piece of the function, so you have to pay attention to which part of the function is covering. There's also a different way you could type it in. You could go ahead and type it in using this type of code and type it into your graphing calculator. It can get a little bit tedious, but again, you still have to supply any holes or filled in values. So you have to make sure that everything is matching up at the critical points here, which are 2 and 4. All right. Another great thing you could do is you can always go ahead and graph it in Desmos. All right. And there's also a way to go ahead and graph it in Desmos. And here's a link to go ahead and do that. And usually the code for it is y is equal to the condition :function, condition :function. All right. And so the same code applies with the graphing calculator, but see, it looks slightly different so that you could go ahead and get those values. But again, you'll need to supply any holes or filled in values just like I did on the graph here. Now, remember that Desmos is also available on your phone, on your mobile devices, so feel free to also download the app to go ahead and do some graphing and test it out. All right, so here we're graphing a piecewise function. All right, and we're looking at values that are surrounded by 2. All right, so we're looking at values that x is equal to 2. All right. And as we look at this, all right, here is our values. It equals 2 up till this value. The limit from the left and right do not match. Okay, so this is a jump type function, but when you graph it, you can actually see it. Now, we don't actually have the function that this involved. So we're going to go ahead and look at an example that actually does include the actual function along with the graph. So here we have a piecewise function where x, when it's less than -1, is 11. X squared plus 2, so it's a partial quadratic here, between -1 and 3 inclusive. And then it is also 11 and x is greater than 3. This is the graph that you're actually going to get in Desmos. And notice we don't have any closed circles or open circles. Those were added in the previous graph. But here at -1 at 11, we know we're going to have an open circle here because x is strictly less than. When we hit the quadratic part of it, the middle section, x squared plus 2 between -1 and 3, that's inclusive. So there's going to be a closed circle at this point here, and there's going to be a closed circle for that piece of the function at here. And then for x greater than 3, it's 11. There's a open circle, but there's already a closed circle in that area. So right over here, that value is going to be included in this piece of the function, but not in this piece of the function, but they definitely do overlap. So here over at -1, all right, we definitely have a jump going on because our limits from both sides do not match. So our limit at -1 is 11 and 3 from the left and from the right, and therefore there is a jump. But we notice at this point here where we have an overlap, there's no discontinuity going on. The graph is continuous at that point. There's an open circle and a closed circle in the exact same spot. If we go ahead and look at another example, here we have a two-piece piecewise function, right? We have 4x plus 4 when x is less than or equal to 0, and a quadratic, x squared minus 4x plus 4 at x greater than 0. All right. And here, because we have the overlap of the less than or equal to and greater than at the exact same point, there are no discontinuities. Our limit matches as it goes ahead and approaches that point 0.